Okay, let's talk about average value. And by average value, we mean the function's average value over some interval. That's the same thing as saying the average height of the function over some interval. And if you just kind of go old school and think of the geometry here, if you wanted the average height, right, the average height of this curve, right, the curve starts out a little low and then goes up and then goes down and then goes up and ends up higher. We want the average height here. Well, the average height, shouldn't it just be the area divided by the width? Shouldn't that give you just the average height? Meaning, if you take this area here in red and divide by the width, which would just be this distance, you'd get the average height. Basically, what you're doing is you're taking the area and you're reforming it into a rectangle. And if you divide the rectangle's area by width, well, then you get the average height. And that's all this calculus formula. Again, if you looked up the calculus formula for average value, it's going to say 1 over b minus a integral from a to b of f of x dx. That would be the formula you'd find. And really, what's it doing? Well, what's this? This is just the area under the curve. And then 1 over b minus a. Well, that's just dividing by b minus a. But what is b minus a? B minus a is the interval. So you're just taking the area and dividing by the width. Again, this is the formula you're going to see if you looked it up. But all it is area and dividing by width. It's the accumulation of something divided by that time interval. And again, I will go through some examples here. Okay, so let's just take a nice function everyone's familiar with. Let's look at sine x. We know that the graph looks something like that. Starts out at 0, goes up and up and up, and goes all the way up to 1, and goes all the way back down. And we know that interval here is pi, right? Sine of pi is 0, and sine of 0 is 0. So let's go from here to here and find the average value of the sine function, right? What's the average height on this graph? And so if we follow this procedure, the average value is going to be 1 over b minus a integral from 0 to pi, right, from a to b of the function. Integrating the function, that's just 1 over pi. Integrating sine, well, the integral of sine is negative cosine. Evaluate from 0 to pi. Okay, that's negative cosine of pi, so that's negative negative 1 minus negative 1. That's just going to be 2. This whole thing is 2, and then 2 times that is just 2 over pi. So we're claiming that the average height there is 2 over pi. Okay, not too bad, right? It's not 1. It's something less than 1. It's kind of like maybe 2 divided by 3.14 is probably something like 0.62 or something. Okay, reasonable, very reasonable that the average height is something like that. It maybe spends a little more time up here than it does down there. Okay, let's kind of go an application this time. I'm going to give you a sense of how this might be useful. Let's say that instead of some abstract function, we had a velocity function. So the velocity was 2t plus 3, and we wanted to find the average velocity, which we might even call v average, from on the interval, I don't know, 2 to 6. Okay, so what would be the average? So the average velocity would then be 1 over 6 minus 2 integral from 2 to 6 of the velocity, 2t plus 3. Okay, so that's just 1 over 4. And then the integral there is going to be t squared plus 3t. Evaluate that from 2 to 6. Okay, so if I plug in 6, I'm going to get 6 squared plus 3 times 6. That's 36 plus 18 is, what, 54? And then 54 plugging in 2. All right, I guess I won't skip any steps here. So that's 54. And then when I plug in 2, I get 4 and 6 I get 10, so that's minus 10, so then that's 1/4 times 44, which is 11. Okay, let's think about what does this mean. Okay, what I said was this is some random curve that might look like something like that, and it's the velocity curve. If we integrated from 2 to 6, we'd be finding this particular area. And what does that area represent on the velocity curve? If you accumulate velocity, this area would represent the displacement, right? In this case, the displacement was this number, 44. The time interval from 2 to 6 seconds is 4 wide. So if we take the area and divide by the width, we get this. And of course this makes sense. If I want to find the average velocity, I could just find how far I went, 44 meters, and divide by on average, or the time interval, 4 seconds, and then get on average what I did, 11 meters per second. Hopefully this makes sense that of course you can accumulate the velocity, divide by the time, and figure out the average velocity. It's no different than up here if I want to find the average of this function, whatever this function might be. If it's some rate, great. Maybe it's the water flowing in and out of a barrel or something. If you integrate the rate, you're going to get the total, and then you can divide by the width, and you get then the average amount. Again, we'll do another example. We kind of look at, let's look at a gallon in a water example, okay? So let's look at f of t. Let's say f of t is 3t squared plus 4, right? And this would be some gallons per minute that's flowing into a pool, okay? And it would look something like this on the graph, right? Some quadratic from, and let's look from 0 to 5. Okay, I have to kind of give you the bounds here. Okay, and what would happen? Well, the average value formula says to take the integral, and we know that's the area, and then divide by the width, right? The average f of t, and the average value of that function is 1 over b minus a integral from a to b of the function, 3t squared plus 4 over time. This is just 1/5. The integral here is going to be t cubed plus 4t evaluated from 0 to 5, right? We have to do the integral. That's 1/5 times, plugging in 5 is going to be 125 plus 20, so that's 145. Plugging in 0 is easy, that's just 0. And I get 1/5 of 145, which is 29. Okay, let's think of the units here. I was trying to find the average function value. The function is how many gallons per minute that's coming in to some pool. So what is 29? What's the average one of these? So this better be gallons per minute as well. It's the average of this. Again, if you look at 0, well, when t is 0, 4 gallons are coming in. When t is 5, we have 79 gallons coming in, right? Obviously, this isn't to scale, right? This graph is 0, 4, and after 5 minutes later, it's 5, 79, right? Certainly the average is somewhere between 4 and 79, but we're not really sure. This is some quadratic. We just can't divide those by 2 and expect to find the average. So what do? Well, we integrate. We accumulate that rate, because what does this 145 represent? This represents the 145. That's how many total gallons came in, right? That's the area here. That's this part of the function. 145 gallons came in that 5-minute span. But if you take the 145 and divide by 5, then you get, on average, how many gallons came in per minute. Again, I just really want to emphasize the fact that the average value formula makes sense. I know in the abstract, it might look a little weird of what you're doing, but all it is, whether it's t or f, or excuse me, t or x, is you're accumulating a function, accumulating some rate to find the total change, and then dividing by the time interval to find then the average rate or the average value of anything. Again, you can integrate acceleration to find acceleration. You can integrate f of t to find the average f of t, or it can just be totally in the abstract. You can integrate f of x, divide by that width to find the average f of x. Okay, so average value of this formula hopefully makes sense both from a calculus perspective of the accumulation divided by width, and also just a geometry, is that this finds the area. Multiplying by this is the same thing as dividing by that width to find average height.